Welcome, everyone. I'm Dr. Ayşe Sunar, and we are going to explore the alchemy of choice today. In the digital age, we are constantly turning the raw, messy user data into something valuable, perfectly timed, and personalized recommendations. But as we'll see, this isn't just a magic. It's a precise blend of psychology, mathematics, and strategic thinking. In 2006, Netflix did something extraordinary. They offered $1 million prize to anyone who could improve their recommendation accuracy by just 10%. Why such a massive bounty for a seemingly small topic? Because while the prize was $1 million, the actual value was billions. Today, Netflix estimates that these algorithms save them over 1 billion every single year by just keeping their users engaged and subscribed. This is where high-level data analytics meets massive business impact. But why do we need these systems at all? It comes down to a psychological concept called the paradox of choice. When we are faced with over 15,000 options, we don't feel empowered, we feel paralyzed. As psychologist Barry Schwartz argued, more is often less. Without a guide, users feel overwhelmed and simply walk away from the platform. Recommender systems are the solution to this fatigue. So technically, a recommender system is a subclass of information filtering that predicts the rating or preference a user would give to an item, whether it's a song on Spotify, a product on Amazon, a film on Netflix. The goal is the same: to bridge the gap between a massive library of content and a unique individual taste. 3 ingredients make this possible. We have users. They are real people with tastes, histories, preferences, values. And we have items, films, friends, anything we can rate or anything we can interact with. And we have ratings. This could be explicit, like giving a film 4 stars, or this could be implicit, like when you pause the film, when you watch to the end, when you abandon the film. There are 2 main approaches to do this. One is content-based filtering. This is asking, what is this item made of? So if you like a sci-fi movie, we will give you more sci-fi movies. But today we are going to focus on collaborative filtering. This doesn't care about the genre of the movie. It finds patterns in behaviors that suggest things you'd like it, even you didn't know it. So collaborative filtering asks, who else has similar taste to you? For example, you watch 3 films and love them. To find what you should watch next, we don't look at the movies. We look for the taste wins. We find Alice, we find Ayesha, we find Dev, we find Lee in your network, and we just realize like Ayesha liked the movie Parasite, and the logic suggests you would love it too. We are using social patterns to predict individual desire. So how does this collaborative filtering actually work? There are 4 main steps. So first, we find similar users. Let's take Alice, look at all the films she's watched and rated, and find other users who rated the same movies in the same way. We call them neighbors. And the second step is measuring similarity in that neighborhood. Not all neighbors are equally similar. We need a number, a score, to tell us how close 2 users' tastes really are. In the second step, we aggregate ratings. We do this for every unseen item and rank the predicted ratings and weight them how similar each neighbor is to Alice. So if the similarity is high, that means we will give more weight to that rating. In the final step, we do recommend top items. So we do for every unseen item, rank the predicted ratings and surface the best ones. This is it, 4 steps. The elegance is step 2. How do we measure similar users? How do we find that exact number? Let's look at the mathematics behind this. So to a computer, our social patterns looks like this matrix. This is a user item matrix. It's a massive grid of numbers, and the rows are users, and the columns are films. So every cell showing the rating from 1 to 5. So the challenge for data scientists is most of these cells are sparse. That means that those are all question marks. So our job is to use the math to predict what those question marks should be. So how do we do that? We use similarity measurements. I'm going to explain the cosine similarity today. The answer involves vectors and an angle. So this is the formula. We calculate the similarity between A and B is dot product of A and B over norm of A times norm of B. Don't be intimidated by the numbers. Let me show you what it means geometrically, and then we will work on the numbers. So we treat users as vectors. You see Alice is the green arrow, and Lee is the yellow arrow. So these are the vectors we put in the multi-dimensional space. The angle between them is very important. We measure that. So it's the cosine similarity. So if these two angles are exactly opposite way, so that means if the angle between them is 180 degrees, that means they are going to opposite directions. That means their tastes are exactly opposite. But if the angle is 0, that means they go to the same direction, and the cosine similarity of angle 0 is 1. That means these two users are identical. So that means if the angle is small, these people are having similar tastes. So look at the numbers. So we represent Alice with her ratings. If there's no rating or if it's a question mark, so we say we treat it as 0. When we do dot product, that means we are multiplying corresponding values and sum this up, and then we get the norms. And when we put all these numbers to the formula, we get a number 0.65. What does it mean? It is close to 1, so that means Alice and Lee have moderately similar preferences. That means they rated many films in the same way, but they also rated some movies differently. So don't focus too much on the arithmetic side, but the key idea here is that we need a principled way to quantify whether two users have similar preferences or not, and cosine similarity is one of the very common way to do that. However, the real world is rarely as clean as the classroom data. We face too many problems. One common problem is cold start problem. How do you recommend something, someone, if they are new to the platform, if they haven't rated anything yet, or a brand new movie nobody has rated yet? And we have sparsity problem. The real life, you are going to find your 99% of your data is actually missing. And in real life, not every user gives ratings to movies. They usually watch and continue. So we have implicit feedback, like when they click, when they pause, when they rewatch. So you need to interpret these weak signals accurately. And we face filter bubble. This is one of the biggest traps. This is a risk of trapping users in an echo chamber of their own past preferences. So you keep giving the same items as a recommendation, and the user just get bored. They are not surprised. They don't find anything interesting there. And also, we need to think about fairness and bias. If we keep recommending popular items, then they will be more popular. But how about less mainstream contents? For example, independent films. For example, minority language songs. So we need to think about these things while giving recommendations. So these aren't just an academic problems. These affects that what millions of people see, hear, and believe eventually. Navigating these hurdles is where the real work of data science begins. So today, in a very short lecture, we've looked at matrices, vectors, and similarity. And I want to leave you with a broader perspective. So as data scientists, we aren't just building engines for engagement. Our task isn't to manipulate the choices, but to provide clarity in a world of noise. So the models we build, they shape what people discover, what they consume, and sometimes even how they see the world. So as you continue your journey in data science, remember that behind every data set is a human impact. Use your skills thoughtfully and ethically, and hopefully we will build systems that don't just capture attention, but truly foster discovery and meaningful connections. Thank you very, very much for today, and hope to see you at Warwick.